Hello everybody, welcome to this new topic, signal processing. Signal processing is an extremely important topic in the context of ADAS. It's more or less a backbone of ADAS. Now before I explain the role and responsibility of signal processing in ADAS context, I'll briefly touch upon what is meant by signal processing. Okay, let me tell you, signal processing is a huge topic. I'm not at all sure that I'm going to do justice to the entire signal processing topic in this 6 or 7 slides, but I will definitely assure you that I will give you a brief idea what is meant by signal processing. Okay, what exactly is meant by signal processing, what exactly is the role of signal processing. I assure you that signal processing is a broad field that involves the analysis, modification and synthesis of signals which are representations of physical quantities that vary with time, space or any other independent variable. Of among all these three, analysis, modification and synthesis, synthesis is the most important word. You synthesize the signals. What is meant by synthesize? Conversion of one signal into another signal. Okay, signals can be audio, images, video, sensor, data, biological signals, communication signals and more. Signal processing techniques are used to extract meaningful information, enhance quality, compress data, filter noise, detect patterns and make decisions based on the signal. Okay, signal processing are the techniques to use to extract meaningful information. Understand this word carefully. So among the entire raw signal, a meaningful information is extracted or derived, okay, and make decisions based on that signal. Now what are the various types of signals? Signals can be classified into different categories. A continuous time versus discrete time signals. You can see on the right side small illustrations which show you the difference between continuous time versus discrete time signals. Continuous time signals are defined for every instant in time. Example, analog audio signals. This is a very common and important example for continuous time signals. Next is discrete time signals are defined only at specific time intervals. Example, digital audio sampled at 44.1 kHz. Next comes the analog versus digital signals. Analog signals are continuous in both time and amplitude. Example, voltage in a microphone. Now, people coming from basic electronic background of course knows analog or digital signals, but coming from mechanical background understand that voltage in a microphone is an analog signal. It is continuous, meaning continuous in both time and amplitude. Now when it comes to digital signals are discrete in both time and amplitude. So I hope everybody understands the difference between continuous and discrete. Digital signals are discrete both in time and amplitude. So in this picture, in this small illustration, you can clearly see the difference between analog and digital signals. And some very common important examples of digital signals are MP3 files, JPEG images. Next comes deterministic versus random signals. Deterministic signals are modeled mathematically, and next random signals have uncertainty. Example, noise in communication channel. Okay, so you understand the various types of signal classifications or categorization? Hope so. Next comes key areas of signal processing. Signal processing are divided into two main categories. Signal processing areas have two main classifications. One is analog continuous signal processing, and it deals with continuous signals. Example, analog filters in radio receivers. Uses resistors, capacitors, inductors and operational amplifiers. Okay, example, RC low pass filter to remove high frequency rate. So this is a very common example, RC low pass filter to remove high frequency noise. So this is a kind of filter which filters off all the high frequency noise. Next kind of signal processing is digital signal processing. This is where we have the main emphasis. The process sampled and digital signals using algorithms performed on computers, microcontrollers and FPGAs and DSP chips. Examples again MP3 compression, image filtering and speech recognition. These are all digital signal processing examples. Fundamental operations in signal processing. Okay, convert signal acquisition and sampling, converting real world signals into digital form using analog to digital converters. So we are going to touch upon the various fundamental operations in signal processing, and the most important fundamental signal processing process is signal acquisition and sampling. Okay, in signal acquisition and sampling, we convert the real world signal into digital form using analog to digital converters. All right, sampling rate must be at least twice the highest frequency to avoid aliasing. Okay, understand this, the sampling rate must be at least twice. Now in case you don't understand, just ignore it. Okay, this is in case you are coming from mechanical background, you don't understand this, just ignore it. This is not exactly very important, this is very basic thing, where if you are pursuing a career in ADAS, you will definitely not go to such a basic level. Okay, I am just explaining this for sake of your understanding. Next is filtering. Low pass filter allows low pass frequencies, blocks high frequencies. Next, what is meant by high pass filter? It blocks low frequencies and allows high frequency. The name itself is self-explanatory. Next is the band pass filter, allows a specific frequency range. Fourier transform and frequency analysis decomposes the signal into frequency components. Alright, this Fourier transform and frequency analysis is a fundamental operation in signal processing which decomposes the signal into frequency components, and it also discrete Fourier transform and fast Fourier transform are widely used. Next comes modulation and demodulation. This is basically used in communication systems, for example AM, FM radio or Wi-Fi. Wi-Fi is something which we use in day-to-day life in our household purpose. Next comes the modulation, embedding information into carrier signal. Demodulation, extracting the original signal. Next comes the compression, reducing data size while retaining essential information. The lossless compression, lossy compression. These are all the various types of compressions. Next is the feature extraction and machine learning, extracting key extractions or characteristics for pattern recognition, and this is also it is used in AI, deep learning and biomedical signal processing. Signal processing has applications in various verticals, not only just automotive, medical, construction, defense, aeronautics, space technology. In all these things, digital signal processing has extreme various variety of applications. Now applications of signal processing. Now let's see the various fields in which signal processing is used. First is the audio processing, which requires noise cancellation, speed recognition and music synthesis. Next is image and video. Image and video comprise of JPEG, MPEG compression, face detection, medical images, even all the MRI scanning, CT scans used in hospitals, which I am sure everybody would have encountered at some point of life, would have used this kind of medical imaging. Next comes the communications. And the communications, well, most of the things are very familiar to in your day-to-day life: 5G, Wi-Fi, radar, satellite communications. And when it comes to biomedical, ECG, EEG, MRI reconstruction, pacemakers, all these come under the category of biomedical. Now let's come to the automotive, which we are interested in. Well, radar, lidar, engine noise analysis, radar signal, lidar signals, all the signals undergoes signal processing so that you can derive the required data. Next comes finance, stock prediction, fraud detection. Even here in finance vertical, signal processing is extensively used. Next comes robotics and artificial intelligence, sensor fusion and autonomous vehicles. Okay, when it comes to robotics and artificial intelligence, this digital signal processing is used in sensor fusion and autonomous vehicles. Now let's see the various types of tools and technologies used for digital signal processing. When it comes to software, MATLAB, Python, TensorFlow, PyTorch, these are all the various types of softwares that are extensively used. And next, when it comes to hardware, DSP processors, lot of DSP processors are available in the market like TIC 6000, FPGAs, GPUs for deep learning. GPU is nothing but graphical processing unit for deep learning. And what are various types of algorithms? These are like plug-in algorithms which can be used or which can be bought off the shelf from the market. Okay, one is FFT, Kalman filters, wavelet transforms, neural networks. These are the various types of algorithms that are used. So in conclusion, signal processing is a fundamental technology that enables modern communication, multimedia, health center and AI systems. It involves acquiring, transforming and interpreting signals to extract useful information efficiently. With advancements in machine learning and real-time processing, its applications continue to grow rapidly. Now what I gave in this particular set of slides, in this particular video, is nothing but scratching the surface of the surface of the surface. It is not by any means extensive or exhaustive. Okay, so this is just giving you a very brief introduction about what is meant by digital signal processing, or rather signal processing. Okay, it has a lot of applications in communications, multimedia, healthcare, AI systems. It involves acquiring, transforming and interpreting signals to extract useful information directly, and with advancements in machine learning and real-time processing, these applications continue to grow rapidly. So these applications are going to further grow in the coming future. All right, thank you.